Okay. Characteristics of polynomial functions. So the standard form of a polynomial function is the same as when we did standard form of a quadratic, where you write the terms from the biggest exponent down to the smallest. You can kind of see an example here. See the biggest exponent, then the next biggest, and then this one is really an exponent of 1. And the 17 is called the constant term. It's also 3x to the 0, because remember x to the 0 is just 1. So these are all written in order from the largest exponent down to the smallest. This is how you write it generally. So a sub n is going to be a constant number. It's the coefficient of x to the n. Plus, this is going to be our next constant number, a sub n minus 1. And then x to the n minus 1. So you'll notice that the exponent is losing a degree each time. This a sub n and a sub n minus 1, they don't necessarily have to go down 1 each time. Notice the coefficients here, they're not going down 1 each time, but the exponents will go down 1 each time. Plus a sub n minus 2 times x to the n minus 2. And this will go on. You know, if your first exponent is like 100, then it will go on. And you'll be able to go all the way down to a sub 1 x to the 1. And then finally your constant term that doesn't have an x.
What is that after the first plus?
So a, and then subscript n minus 1. And then over here, a and subscript n minus 2. This is just the general form. It is good to get used to looking at the general form of equations, because often they use things like this on the SAT or on an SOL. And it's good to know what you're looking at. Yes? I will try with my high-powered Zoom tool here. Is it better? There's a lot of seats up front. Like, if you want to move up front so that you can see better, you can. The third x?
Yeah,
So it says, then this is plus a sub n minus 2 times x to the n minus 2.
No, like on top of the x.
N minus 1.
Okay, thank you.
Morning. Okay. So this is our example, and then here are some rules. All of the coefficients must be real numbers. What's an example of a number that's not real? I, right. So you can't have I as a coefficient. It says circle the coefficients. So the first one here, see, I don't have a number, but I have a negative, so I know the first one is going to be negative 1. Circle the coefficients of the other terms. Compare with your neighbor and see if you're getting the same thing. Okay, so you should have circled the positive 4, the negative 1/5. Remember that the negative will stay with that number, and even the 17 is a coefficient even though it doesn't have like an x next to it. It says all the exponents must be whole numbers. So the coefficients can be a fraction, but the exponents can't be a fraction. The exponents have to be whole numbers. So you can see you've got 3, you've got 2, and here we have an exponent of 1. So circle your exponents. The degree of the polynomial is the highest exponent. So in the example here, what number is the highest exponent? 3. So that means that the degree is 3. The leading coefficient is the coefficient of the term with the highest exponent. So not necessarily the biggest coefficient, it's the coefficient of the term with the biggest exponent. So we said this is the biggest exponent. What is the coefficient of this term? One person knows. Anybody else know? Some of you guys are spacing out on me. Is -1 the coefficient of this term? It is. So you don't see a number, so you put the 1 in, and the negative's already there. Yeah. So the leading coefficient, and that's a lot to write, so I just write LC. Leading coefficient is -1. The constant term is the y value of the y-intercept. Now remember that the y-intercept is when you put 0 for all your x's. So if I have 0 here, and 0 here, and 0 here, I'm just left with this one. So the constant term is also the term that has no x. And then it's good to know that the constant term is also the y-intercept. I have a highlighter. I'll highlight that. I don't know what I do with it. Okay. So y-intercept is the constant term, which is also the term without the x. And in this one, it is 17. All right, before we describe the shapes, I want to try some problems down here. I think I need to give you some more information for type. The type of the polynomial is going to be a name. It's down here. The type of a polynomial is going to be a name, and I'm just going to make a little space down here to write this, okay? So, degree, D is for degree. I can write it, I think. Degree, and then type. So if the degree is 1, then it's a linear function. If the degree is 2, talk to your neighbor, tell them what kind of function is it if the degree is 2, if your biggest exponent is 2. More talking. Starts with a Q. I heard 2 people say quadratic. You are right. Quadratic. All right, degree is 3. We talked about this function in our last unit. Yeah, cubic. Degree is 3 is cubic. And then after that, they're going to be new to you. 4 is called quartic. And 5 is called quintic. And after that, we don't really use special names for them. You'll just say like a 6th degree polynomial, a 7th degree polynomial. I do think that there exist some names for them, but we just don't use them because we don't have polynomials of that degree very often. All right, so are the following functions polynomials? If yes, write in standard form, state the degree and type, state the constant term, and state the leading term. And if no, say why not. So we're going to do 1 and 2 together, and then you guys are going to do 3 and 4. All right, in number 1, to check and see if it's a polynomial, we need to see if all the coefficients are real numbers. So 6, 3, and 2. Are they all real? Yeah. All the exponents have to be whole numbers. They can't be negative or fractions. Are our exponents good? No, right? Because we have a negative exponent. So it's not a polynomial. Oh, thank you. Not a polynomial. Because of the negative exponent.
So you wouldn't just use 2 as the highest?
No. So, no. It said if it's a polynomial, if yes, then we answer all these questions, and if not, we just have to say why not. All right, then we're going to look at problem 2. Problem 2. Are the coefficients real numbers? 4, 1/2, -1, -5. Are they all real? Yeah, they're all real. Exponents, are the exponents positive whole numbers? Yes. Okay. So, this one, I'm going to use the space over here. So this is a yes for number 2. And then it says to write it in standard form. So I'm going to start with y equals, and I need the term with the biggest exponent, which is the 4. So negative x to the 4. Then my next exponent is 3 plus 1/2 x to the 3. Then I've got x to the 1, so plus 4x to the 1. And then minus 5. That's the standard form. Just writing them in order from the biggest exponent to the smallest. Then it says state the degree and type.
Wait, what did you say we write it in what order?
From the biggest exponent to the smallest exponent. Okay, so your degree is your biggest exponent, which is what number?
4.
Yep, degree is 4, which makes it quartic. Okay, it asks for the constant term. The constant term is the one without an exponent, so that would be, I'm sorry, without an x, so that would be the -5. And it asks for the leading term. So the leading term is the term with the biggest exponent. Leading term is -x to the 4. When you're doing your delta math at home, sometimes it will ask you for the leading term like that, and sometimes it will ask you for the leading coefficient. And the leading coefficient would just be that number in front, -1.
Wait, so what is the leading term?
The leading term is the whole term with the biggest exponent. So you can see the biggest exponent was 4, and then this is the whole term. All right, I think that answers all of the questions. So now you guys are going to do 3 and 4. The first thing is it a polynomial? If it's not, you have to say why not. If it is a polynomial, then you're going to answer all the questions.
Yes.
All right, guys. Were both of these yes, 3 and 4? Which one's a no? 4 is a no because of what? Which exponent made 4 a no?
All 3.
Yeah, the exponent on the 3. So the 3 to the x, that exponent made it not a polynomial. Actually made it like an exponential. Actually, it's kind of a mixture of an exponential and a polynomial, but it's not a polynomial. So this one was not a polynomial. Because of the variable exponent. All right, I am going to ask each group to share something. So be ready with something that you want to share. And if you are worried about something later, then volunteer early on. Standard form. So we said this is yes, right? Standard form. Raise your hand if you would like to share that one. Sal.
-3x with the exponent 5 plus 4x with the exponent of 3. 2x squared root plus 1.
Plus 1. And I'm just going to put the y equals in front and you're good.
Yes.
Okay, no, it's very good. So notice that negative, it stuck on the 3 and everything else was positive. Do you guys have any questions on your standard form? Okay, the next one we're doing is degree. Raise your hand if you want to share the degree. Omar. Anybody else get a degree of 5? Okay, good. Degree is 5. Okay, raise your hand if you would like to tell us the type. Eddie. Quintic. Good. All right, so if you got here late, we do have like a little list of types over here. I'll show that again in a minute. Okay, degree type. We need to know the constant term. Raise your hand if you have the constant term. I see 2, 3 hands. Drew.
Is it 1?
Constant term is 1. Good. Constant equals 1. And leading term. Raise your hand if you have the leading term. Nyla.
Negative 3x.
Leading term equals negative 3x to the 5. Good.
Oh, we've got 2 5.
Oh yeah, I thought you said that part. All right, any questions on that? Okay, I'm just going to show those degree types again for people who came in late, and we'll start on the back in just a minute. Oh yeah, we have to go over the graphs. My bad. We still have to do the graphs. Okay. The constant term is just going to be y equals a number. And it can be any number. Do you guys remember we did this when you were graphing your initials? If you wanted a flat line, it would just like be y equals 5 or y equals 10 or something like that. We say y equals c, the constant term, so whatever that is, okay? And it will make a flat line that goes straight across. For linear, the parent function is y equals x. Remember we did like y equals 1x plus 0, which simplifies to y equals x. And that's going to be a line where the x and y values are the same. And then quadratic, the parent is y equals x squared, which remember that gives you that parabola shape. After that, the parents are like a little bit less helpful in understanding what the graph might look like. And I'll show you why in just a second. So the cubic parent is y equals x cubed. And it looks like this. You probably saw this when you were graphing the inverse of the cube root function. But a cubic function can actually have more terms than that. So y equals x to the third. Looks like that. But say I wanted to just add more to it, like x squared. Maybe I want to make that a 2x squared. You see? So if you make it longer, you see how it can touch the graph 2 times, or I can do -1 like that. Now it touches the x-axis 3 different times. So what we're going to do is we're going to learn about the fundamental theorem of algebra today. And the fundamental theorem of algebra says that the degree tells you how many roots this function has, and the roots are the x-intercepts here. So you can see it can cross 3 times like that, okay? I'm going to write this one on the side as a second example. It's not the parent function, but it really gives you a better idea of what your cubic function might look like. So I have y equals x cubed plus x squared minus 1, and I'm going to show you in a minute, but I'm just copying this graph. Okay. All right, so you can see that a cubic graph might actually cross 3 times.
Will it only ever cross 3?
It won't cross more than 3. The fundamental theorem of algebra tells us that. But like you saw, it could have 1 cross and 1 bounce, or it could be this too. And this function does actually have 3 roots. They're just all 0, which is weird to say the answers are 0, 0, and 0, but they are. So a quartic function is y equals x to the 4, and it looks like a little bit flatter version of the y equals x squared, I believe. Let's look at it real quick. Turn that one off. Y equals x to the 4. Yeah, see how it's like a quadratic, but it's like flat on the bottom? So So that's this, but that we're almost never going to graph that function, because what we're going to graph instead is we're going to graph a function that has 4 roots to it, right? So it's going to be like this, but it's going to have 4 roots, and I won't bother like looking for a particular one, but 1, 2, let's see, 1, 2, 3, 4. So like this W shape is a quartic. So the quartic might look like this, but more often it's going to look something like this. Okay, the quintic, it looks a lot like the cubic one. But again, usually what's going to happen is you're going to have 5 roots. So it could be 1, 2, 3, 4, 5, like that. So every line is just going to look like a straight line. Every quadratic is going to have that one turn in it. But once you get higher in degree, cubic, quartic, and quintic, it could be a very simple graph, or it could be a graph with lots of turns in it.
Can you show quintic one more time with the parent function?
Quintic, this one?
Yeah, on Desmos.
Oh, sure. I don't think I did that one on Desmos. I did quartic. See, it's like the cubic, but it's just a little flatter in the middle. Then if I add this to it, then it can have more turns in it. It can cross up to 5 times. This one doesn't. All right, so now I think we're done with the first page. Do you guys have any questions before we turn?
Ms. Roll,
Yes.
is there one specific line that you're supposed to do
For
for
quartic?
Yeah.
I just showed you one that has 4 crossings, but this is, the quartic will look like, the parent function looks like this parabola that has like a flat bottom to it. But more often our graph is going to look like this. 4 times it crosses the x-axis. All right, when you're ready, turn the page. Let's look at the back. We have the fundamental theorem of algebra. It's kind of weird that you have made it through a year algebra 1 and then half a year of algebra 2 without knowing the fundamental theorem of algebra, but now you get to learn it right here. All right, p of x is a polynomial of degree n greater than or equal to 1. So it's not just a constant term, okay? Then p of x equals 0 has exactly n roots, including repeated roots and also non-real, which are imaginary roots. So remember, like the quadratic, when we solved it, sometimes the roots were imaginary, but we had 2 imaginary roots. Remember, roots are also called zeros. They are the solutions to the equation p of x equals 0. We can identify real roots or zeros on the graph as x-intercepts. So where they cross the x-axis, those are the roots, the zeros, the solutions. Non-real, imaginary roots always come in pairs, and we don't see them on the graph. So if you had, for example, a quadratic that did not cross the x-axis, then those would mean that the 2 roots are imaginary because you can't see where they cross. The fundamental theorem of algebra can be boiled down to this simple statement. The degree of the function is equal to the total number of roots. Okay, the turning points are whenever you have a minimum or a maximum on your function. So the turning points can be the max or the min. And I want you to notice that this has 1, 2, 3, 4 roots. So it could be a 4th degree polynomial. Sorry, the roots are where you cross the x-axis. 1, 2, 3, 4 roots, right? So it could be a 4th degree polynomial. And it has how many turning points? How many times does it switch between increasing and decreasing? 3, yes. So the turning points will be 1 less than the degree. Sometimes you'll have fewer than that. That's why it says it has up to this many turning points. So it's n minus 1. So if the degree is 4, it can have it maximum it can have is 3 turning points.
What does M stand for?
The degree. So if the degree is n, it has 1 less than n turning points. For example, if the degree is 3, this is just an example. If the degree is 3, then it has 3 roots and at most 2 turning points. Remember I showed you the shapes on the other side, and I showed you that quartic, right? That quartic only had 1 turning point, but it could have had 3 turning points. All right, we're going to do one of these together, and then you guys are going to do one on your own. So make sure that you're understanding. Okay, we just counted the turning points here. We counted 1, 2, 3, right? And we counted 4 roots, so we're going to say that the degree is 4, which makes it what? Linear? What is it? Quartic, good. All right, for the domain and range, we do have to understand that there are arrows at the end here. And I can see that the arrows are going up, but they will also be going left and right. Just very slowly, they're going left and right. So my domain is negative infinity to infinity. And that's actually the domain of every polynomial. So if that's a question on a quiz, you know the answer is negative infinity to infinity. You're going to have, sometimes you'll have graphs where one end goes up and one end goes down, and so that will also be your range, but that's not the case in this graph. In this graph, you want to look at the bottom of your graph for the smallest y value. It looks like about -6 to me. You guys reading the same number? Okay. So our range is going to start at -6. You need to include it with a square bracket. And then you're going to go all the way up to positive infinity. So remember, domain is x and range is y. All right, increasing and decreasing intervals are a bit of an ordeal when we do these. So my advice to you is to find your turning points, connect them to the x-axis. We always use x numbers for increasing and for decreasing. So to help us focus on the x-axis, I'm going to start by putting a negative infinity on the left and a positive infinity on the right. And then I'm going to connect each turning point to the x-axis. It's hard to read these graphs. There's probably actually some decimals in here that I'm not seeing, but I did my best to connect them. And so the first interval is going to be going from here to here. And as I follow the graph, am I increasing or decreasing? Yes. So first is going to be a decreasing interval. Increasing and decreasing, always use parentheses. It starts decreasing at negative infinity. And then it keeps decreasing until I get to this number here, which looks to be -3 to me. Are you guys okay with making that a -3? Okay. So it decreases from negative infinity until here. It's like this point right here, with an x value of -3. Then it has a really short increasing interval, picking up at the same place where we left off at -3, and it looks like -1.5 because it's between those two zeros. Okay? So I'm going to go -3 to -1.5. We're increasing. All right, so decreasing, increasing, decreasing. It's picking up at the -1.5 again, and it decreases over here. I'm going to call that a 2, but if you wanted to call it a 1.5, I wouldn't fight you on that. And then finally, at the end, it's increasing again, and it's increasing from the same point where you left off to up to infinity. All right, so increasing and decreasing intervals, it's a lot to determine. You just want to connect to the x-axis to find the numbers that you want. The end behavior, both ends are going up, right? So first we'll talk about the right side. On the right side, as x goes to infinity, the y is going up, so the y is going to infinity. On the left side, as x goes to negative infinity, the y is going up, so the y is going to positive infinity again, my bad. So both of the y's are positive, and then the x's are right side positive and then left side negative. All right, we saw 4 real roots on the x-axis, so they're all real. If, for example, I had like 7 turning points, but I only had 3 real roots, then I would know that there was going to be more roots that were imaginary. But in this case, they're all real roots. So I have 0 non-real roots. State the zeros from the graph. So we're going to say, where does that graph cross the x-axis? I'm going to use fancy brackets to indicate a set of numbers. So I've got -4, -2, and -1. You guys, my eyes are really old, so you tell me if I'm seeing those numbers wrong. And 3. You guys agree with all those?
Yeah.
It's where it crosses the x-axis. Okay. All right, so I'm going to give you a few minutes to work on this section down here. I do want you to work with people in your group. If you have nobody in your group, move yourself so that you have somebody to work with, okay? I'm just going to record these last answers.
All you would be doing, you
I
could
really
like
want
bring a
the
friend
waffle.
if you want. Actually, that'd be